Chapter 15, Part 3 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jairus Amar. Airplane Flying Handbook by the FAA. Low-speed flight. The jet airplane wing, designed primarily for high-speed flight, has relatively poor low-speed characteristics. As opposed to the normal piston-powered airplane, the jet wing has less area, a lower aspect ratio, long chord/short span, and thin airfoil shape, all of which amount to less lift. The swept wing is additionally penalized at low speeds because the effective lift, which is perpendicular to the leading edge, is always less than the airspeed of the airplane itself. In other words, the airflow on the swept wing has the effect of persuading the wing into believing that it is flying slower than it actually is. But the wing consequently suffers a loss of lift for a given airspeed at a given angle of attack. The first real consequence of poor lift at low speeds is a high stall speed. The second consequence of poor lift at low speeds is the manner in which lift and drag vary with speed in the lower ranges. As a jet airplane is slowed toward its minimum drag speed, VMD or L/D max, total drag increases at a much greater rate than lift, resulting in a sinking flight path. If the pilot attempts to increase lift by increasing pitch attitude, airspeed will be further reduced, resulting in a further increase in drag and sink rate as the airplane slides up the backside of the power curve. The sink rate can be arrested in one of two ways. Pitch attitude can be substantially reduced to reduce the angle of attack and allow the airplane to accelerate to a speed above VMD, where steady flight conditions can be reestablished. This procedure, however, will invariably result in a substantial loss of altitude. Thrust can be increased to accelerate the airplane to a speed above VMD to reestablish steady flight conditions. It should be remembered that the amount of thrust required will be quite large. The amount of thrust must be sufficient to accelerate the airplane and regain altitude lost. Also, if the airplane has slid a long way up the backside of the power required drag curve, drag will be very high and a very large amount of thrust will be required. In a typical piston engine airplane, VMD in the clean configuration is normally at a speed of about 1.3 Vs. See Figure 15-12. Flight below VMD on a piston engine airplane is well identified and predictable. In contrast, in a jet airplane, flight in the area of VMD, typically 1.5 to 1.6 Vs, does not normally produce any noticeable changes in flying qualities, other than a lack of speed stability, a condition where a decrease in speed leads to an increase in drag, which leads to a further decrease in speed and hence a speed divergence. A pilot who is not cognizant of a developing speed divergence may find a serious sink rate developing at a constant power setting, and the pitch attitude that appears to be normal. The fact that drag increases more rapidly than lift, causing a sinking flight path, is one of the most important aspects of jet airplane flying qualities. Stalls. The stalling characteristics of the swept-wing jet airplane can vary considerably from those of the normal straight-wing airplane. The greatest difference that will be noticeable to the pilot is the lift developed versus angle of attack. An increase in angle of attack of the straight wing produces a substantial and constantly increasing lift vector, up to its maximum coefficient of lift, and soon thereafter, flow separation, stall, occurs with a rapid deterioration of lift. By contrast, the swept wing produces a much more gradual buildup of lift, with no well-defined maximum coefficient, and has the ability to fly well beyond this maximum buildup, even though lift is lost. The drag curves, which are not depicted in Figure 15-13, are approximately the reverse of the lift curves shown, in that a rapid increase in drag component may be expected with an increase in the angle of attack of a swept-wing airplane. The differences in the stall characteristics between a conventional straight-wing / low tailplane non-T-tail airplane and the swept-wing T-tail airplane center around two main areas: the basic pitching tendency of the airplane at the stall, tail effectiveness in stall recovery. On a conventional straight-wing / low tailplane airplane, the weight of the airplane acts downwards, forward of the lift acting upwards, producing a need for balancing force acting downwards from the tailplane. As speed is reduced by gentle up elevator deflection, the static stability of the airplane causes a nose-down tendency. This is countered by further up elevator to keep the nose coming up and the speed decreasing. As the pitch attitude increases, the low-set tail is immersed in the wing wake, which is slightly turbulent, low-energy air. The accompanying aerodynamic buffeting serves as a warning of impending stall. The reduced effectiveness of the tail prevents the pilot from forcing the airplane into a deeper stall. See Figure 15-14. The conventional straight-wing airplane conforms to the familiar nose-down pitching tendency at the stall and gives the entire airplane a fairly pronounced nose-down pitch. At the moment of stall, the wing wake passes more or less straight rear wind and passes above the tail. The tail is now immersed in high-energy air, where it experiences a sharp increase in positive angle of attack, causing upward lift. This lift then assists the nose-down pitch and decrease in wing angle of attack, essential to stall recovery. In a swept-wing jet with a T-tail and rear fuselage-mounted engines, the two qualities that are different from its straight-wing, low tailplane counterpart are the pitching tendency of the airplane as the stall develops, and the loss of tail effectiveness at the stall. The handling qualities down to the stall are much the same as the straight-wing airplane, except that the high T-tail remains clear of the wing wake and provides little or no warning in the form of a pre-stall buffet. Also, the tail is fully effective during the speed reduction towards the stall, and remains effective even after the wing has begun to stall. This enables the pilot to drive the wing into a deeper stall at a much greater angle of attack. At the stall, two distinct things happen. After the stall, the swept-wing T-tail airplane tends to pitch up rather than down, and the T-tail is immersed in the wing wake, which is low-energy turbulent air. This greatly reduces tail effectiveness and the airplane's ability to counter the nose-up pitch. Also, the disturbed, relatively slow air behind the wing may sweep across the tail at such a large angle that the tail itself stalls. If this occurs, the pilot loses all pitch control and will be unable to lower the nose. The pitch up just after the stall is worsened by large reduction in lift and a large increase in drag, which causes a rapidly increasing descent path, thus compounding the rate of increase of the wing's angle of attack. See Figure 15-15. The pitch-up tendency after the stall is a characteristic of a swept and or tapered wings. With these types of wings, there's a tendency for the wing to develop a strong spanwise airflow towards the wingtip when the wing is at high angles of attack. This leads to a tendency for separation of airflow, and the subsequent stall to occur at the wingtips first. See Figure 15-16. The tip-first stall results in a shift of the center of lift of the wing in a forward direction relative to the center of gravity of the airplane, causing the nose to pitch up. Another disadvantage of a tip-first stall is that it can involve the ailerons and the road roll control. As previously stated, when flying at a speed in the area of VMD, an increase in angle of attack causes drag to increase faster than lift, and the airplane begins to sink. It is essential to understand that this increasing sinking tendency at a constant pitch attitude results in a rapid increase in angle of attack as the flight path becomes deflected downwards. See Figure 15-17. Furthermore, once the stall has developed and a large amount of lift has been lost, the airplane will begin to sink rapidly, and this will be accompanied by a corresponding rapid increase in angle of attack. This is the beginning of what is termed a deep stall. As an airplane enters a deep stall, increasing drag reduces forward speed to well below normal stall speed. The sink rate may increase to many thousands of feet per minute. The airplane eventually stabilizes in a vertical descent. The angle of attack may approach 90 degrees, and the indicated airspeed may be reduced to 0. At a 90-degree angle of attack, none of the airplane's control surfaces are effective. It must be emphasized that this situation can occur without an excessively nose-high pitch attitude. On some airplanes, it can occur at an apparently normal pitch attitude, and it is this quality that can mislead the pilot because it appears similar to the beginning of a normal stall recovery. Deep stalls are virtually unrecoverable. Fortunately, they are easily avoided as long as published limitations are observed. On those airplanes susceptible to deep stalls, not all swept and/or tapered wing airplanes are. Sophisticated stall warning systems such as stick shakers and stick pushers are standard equipment. A stick pusher, as its name implies, acts to automatically reduce the airplane's angle of attack before the airplane reaches a fully stalled condition. Unless the airplane flight manual procedures stipulate otherwise, a fully stalled condition in a jet airplane is to be avoided. Pilots undergoing training in jet airplanes are taught to recover at the first sign of an impending stall. Normally, this is indicated by aural stall warning devices and/or activation of the airplane stick shaker. Stick shakers normally activate around 107% of the actual stall speed. At such slow speeds, very high sink rates can develop if the airplane's pitch attitude is decreased below the horizon, as is normal recovery procedure in most piston-powered straight-wing light airplanes. Therefore, at the lower altitudes where plenty of engine thrust is available, the recovery technique in many swept-wing jets involves applying full available power, rolling the wings level, and holding a slightly positive pitch attitude. The amount of pitch attitude should be sufficient enough to maintain altitude or begin a slight climb. At high altitudes, where there may be little excess thrust available to effect a recovery using power alone, it may be necessary to lower the nose below the horizon in order to accelerate away from an impending stall. This procedure may require several thousand feet or more of altitude loss to effect a recovery. Stall recovery techniques may vary considerably from airplane to airplane. The stall recovery procedures for a particular make and model airplane, as recommended by the manufacturer, are contained in the FAA-approved Airplane Flight Manual for that airplane. Drag devices. To the pilot transitioning into jet airplanes, going faster is seldom a problem. It is getting the airplane to slow down that seems to cause the most difficulty. This is because of the extremely clean aerodynamic design and fast momentum of the jet airplane, and also because the jet lacks the propeller drag effects that the pilot has been accustomed to. Additionally, even with the power reduced to flight idle, the jet engine still produces thrust, and deceleration of the jet airplane is a slow process. Jet airplanes have a glide performance that is double that of piston-powered airplanes, and jet pilots often cannot comply with an air traffic control request to go down and slow down at the same time. Therefore, jet airplanes are equipped with drag devices such as spoilers and speed brakes. The primary purpose of spoilers is to spoil lift. The most common type of spoiler consists of one or more rectangular plates that lie flush with the upper surface of each wing. They're installed approximately parallel to the lateral axis of the airplane and are hinged along the leading edges. When deployed, spoilers deflect up against the relative wind, which interferes with the flow of the air about the wing. See Figure 15-18. This both spoils lift and increases drag. Spoilers are usually installed forward of the flaps, but not in front of the ailerons, so as not to interfere with roll control. Deploying spoilers results in a substantial sink rate with little decay in airspeed. Some airplanes will exhibit a nose-up pitch tendency when the spoilers are deployed, which the pilot must anticipate. When spoilers are deployed on landing, most of the wing's lift is destroyed. This action transfers the airplane's weight to the landing gear, so that the wheel brakes are more effective. Another beneficial effect of deploying spoilers on landing is that they create considerable drag, adding to the overall aerodynamic braking. The real value of spoilers on landing, however, is creating the best circumstances for using wheel brakes. The primary purpose of speed brakes is to produce drag. Speed brakes are found in many sizes, shapes, and locations on different airplanes, but they all have the same purpose: to assist in rapid deceleration. The speed brake consists of a hydraulically operated board that, when deployed, extends into the airstream. Deploying speed brakes results in a rapid decrease in airspeed. Typically, speed brakes can be deployed at any time during flight in order to help control airspeed, but they are most often used only when a rapid deceleration must be accomplished to slow down to landing gear and flap speeds. There is usually a certain amount of noise and buffeting associated with the use of speed brakes, along with an obvious penalty in fuel consumption. Procedures for the use of spoilers and/or speed brakes in various situations are contained in the FAA-approved Airplane Flight Manual for the particular airplane. Thrust reversers. Jet airplanes have high kinetic energy during the landing roll because of weight and speed. This energy is difficult to dissipate because a jet airplane has low drag with the nose wheel on the ground, and the engines continue to produce forward thrust with the power levers at idle. While wheel brakes normally can cope, there is an obvious need for another speed retarding method. This need is satisfied by the drag provided by reverse thrust. A thrust reverser is a device fitted in the engine exhaust system which effectively reverses the flow of the exhaust gases. The flow does not reverse through 180 degrees. However, the final path of the exhaust gases is about 45 degrees from straight ahead. This, together with the losses in the reverse flow paths, results in a net efficiency of about 50%. It will produce even less if the engine RPM is less than maximum in reverse. Normally, a jet engine will have one or two types of thrust reversers, either a target reverser or a cascade reverser. See Figure 15-19. Target reversers are simple clamshell doors that swivel from the stowed position at the engine tailpipe to block all of the outflow and redirect some component of the thrust forward. Cascade reversers are more complex. They are normally found on turbofan engines, and are often designed to reverse only the fan air portion. Blocking doors in the shroud obstructs forward fan thrust and redirects it through cascade vanes for some reverse component. Cascades are generally less effective than target reversers, particularly those that reverse only fan air, because they do not affect the engine core, which will continue to produce forward thrust. On most installations, reverse thrust is obtained with the thrust lever at idle, by pulling up the reverse level to a detent. Doing so positions the reversing mechanisms for operation, but leaves the engine at idle RPM. Further upward and backward movement of the reverse lever increases engine power. Reverse is cancelled by closing the reverse lever to the idle reverse position, then dropping it fully back to the forward idle position. This last movement operates the reverser back to the forward thrust position. Reverse thrust is much more effective at high airplane speed than at low airplane speeds, for two reasons. First, the net amount of reverse thrust increases with speed. Second, the power produced is higher at higher speeds, because of the increased rate of doing work. In other words, the kinetic energy of the airplane is being destroyed at a higher rate at the higher speeds. To get maximum efficiency from reverse thrust, therefore, it should be used as soon as is prudent after touchdown. When considering the proper time to apply reverse thrust after touchdown, the pilot should remember that some airplanes tend to pitch nose up when reverse is selected on landing, and this effect, particularly when combined with the nose-up pitch effect from the spoilers, can cause the airplane to leave the ground again momentarily. On these types, the airplane must be firmly on the ground with the nose wheel down before reverse is selected. Other types of airplanes have no change in pitch, and reverse idle may be selected after the main gear is down and before the nose wheel is down. Specific procedures for reverse thrust operation for a particular airplane/engine combination are contained in the FAA-approved Airplane Flight Manual for that airplane. There is a significant difference between reverse pitch on a propeller and reverse thrust on a jet. Idle reverse on a propeller produces about 60% of the reverse thrust available at full power reverse, and is therefore very effective at this setting when full reverse is not needed. On a jet engine, however, selecting idle reverse produces very little actual reverse thrust. In a jet airplane, the pilot must not only select reverse as soon as reasonable, but then must go up to full power reverse as soon as possible. Within airplane flight manual limitations, full power reverse should be held until the pilot is certain the landing roll will be contained within the distance available. Inadvertent deployment of thrust reversers is a very serious emergency situation. Therefore, thrust reverser systems are designed with this prospect in mind. The systems normally contain several lock systems, one to keep reversers from operating in the air, another to prevent operation with the thrust levers out of idle detent, and/or an auto stow circuit to command reverser stowage at any time unwanted motion is detected. It is essential that pilots understand not only the normal procedures and limitations of thrust reverser use, but also the procedures for coping with uncommanded reverse. Those emergencies demand immediate and accurate response. End of Chapter 15, Part 3. Recording by Jairus Amar.